These are the notes on chemistry, kind of the basic stuff. We're just going to start getting into the subject of chemistry after having completed our warm-ups. You know what to do. If you can hear me, I guess you've already done these things. So Chemistry A, the first part of chemistry, can be a challenging class. It's going to start off with some easy stuff, and then it's going to build. So just keep up with the easy stuff. Don't just blow it off, okay? Pay attention, learn it, and that'll be the foundation for what we do later. Chemistry builds and builds all the way through Chemistry B, and it is considered one of the harder classes in high school, but you can do very well if you keep up. So if you find some of the early stuff very easy, don't be surprised, but you got to brace yourself for the more challenging concepts later. It's important to know what chemistry is, so I'm just going to give you the definition. In a nutshell, the simplest definition is chemistry is the study of matter and how it behaves and interacts. So matter is really everything. So chemistry is a very, very broad subject. It isn't really limited to people with lab coats in laboratories doing little experiments with beakers and test tubes and flasks. It's actually trying to understand everything, the whole kind of universe. So you're going to find that chemistry gives you insight into the whole world around you. A lot of times when there's an important key concept, I make a little call out placard like this, and in class I hold them up. A placard like this is the very simple idea that you need to definitely know. So chemistry is the study of matter. That's the simplest way to say it. Now I've got to give you a caveat, a little asterisk here at the beginning. We don't know what dark matter is. So at this point, there's a lot of chemistry we have yet to learn. No one in the world understands what dark matter is. We can only speculate, and I'd rather not speculate right now. So just keep in mind, I don't want to give the impression that we've got it all sewn up. We understand everything. We do not. We clearly do not. In fact, we are aware of our lack of understanding because we know dark matter is there. We can see its imprint, and yet we don't understand what it is. So it's good to realize that we don't know everything. So we're going to work on the things that we do understand. And if you were to take chemistry maybe 50 years in the future, who knows? There might be a dark matter unit in it. But at this point, we don't know. So this goes through the whole course. Just keep in mind, take it with a grain of sodium chloride, that we do not know everything. Chemistry is fairly ancient. If you go all the way back to the ancient Greeks, they had kind of the very beginnings of chemistry. They couldn't really examine things with a lot of equipment. They had very simple apparatus. So they thought about things and they came up with some of the basic concepts. The Greek word for chemistry, as you see written there with those Greek letters, is chemia, starting with that X, that's actually a chi, okay, in Greek. Chemia was the original word they used to try to understand matter. Then, of course, there were the Dark Ages. In the Dark Ages, all of the learning the Greeks had done was translated into Arabic. And when you translate chemia into Arabic, they put a little al on the front, which is like a the in Arabic, and it became alchemia. Okay? Now that gives us the word alchemy. So in the early days, chemistry was alchemy. Although nowadays they differentiate alchemy from chemistry because alchemy was pre-scientific. It didn't use the scientific method. It wasn't rigorous. It wasn't a shared cooperative methodology using empirical data. So when we say the word alchemy, well, some of the things we still use today come from that era. Think of the alchemist in the top picture trying to make gold out of mercury or something. Not the ones on the bottom, the anime version, the Full Metal Alchemist, not that one. But the point is, alchemy had a big impact on chemistry. And some of the early chemists, even Robert Boyle, some of the early great chemists, started off as alchemists. They would have even considered themselves alchemists, at least at some point. So chemistry is the study of matter. So what is matter? Ice cream is matter. The cup that the ice cream is in is matter. The air around that is matter. Matter comes in lots of different varieties and flavors, like Baskin-Robbins purportedly has 31. So I wonder how many flavors there are of matter. Perhaps there are 31, just like Baskin-Robbins. Maybe they use all of them. Or maybe there's 57, like Heinz, ketchup, what else do they have? Mustard and relish. I guess that's 3. They purportedly have 57. I think they made that up. How many flavors of matter are there? Well, turns out there is an answer. There are 118 different flavors of matter. What am I talking about? You should think about this for a moment. If it doesn't occur to you, what are there 118 of? Oh yeah, the periodic table, the elements. There are 118 different elements. Those are the flavors of matter, and you should not eat them all. You should not eat cesium. You should not eat mercury or potassium, not in its elemental form at least. But I'm calling them flavors. Okay. So those are the kinds of matter, and then of course, just like the ice cream, you can put together more than one kind of ice cream. You could take 2 different flavors and put them in the same cup. That's a compound. So we're going to be learning about all those flavors of matter. It's a good thing for us that there are not thousands of them or millions of them. That would make chemistry really untenable. You couldn't really do it. But with 118, you know what? We can deal with that. And not only is it a small number, we can chop them into groupings, which makes the number even smaller. We can look for families of elements. When we talk about a chemical reaction, some of them are very, very flashy. Some of them are very, very dramatic. Okay, like this one. Fireworks are a chemical reaction. Now, mostly fireworks are essentially all the same reaction. There are actually different ways of doing it, but primarily it's this reaction on the bottom, which we call the decomposition of potassium nitrate. Now, fireworks are made of chemicals, but then during the reaction, the chemicals change. Notice the chemicals on the left side, KNO3, change to something else on the right side. It's not the same chemical. So a chemical is anything that has a definite composition. Something you could write like KNO3. If you can write it like that, it's a chemical. What's another thing we could write like that? What's the chemical formula for water? That's the most famous one in the world, I believe. You probably know it. H2O. So if you could write it like that, H2O, it's a chemical. Now, not all chemicals are hazardous. Not all chemicals are dangerous. In fact, some are essential for living, like water, oxygen, O2. So chemicals get a bad rap. They get a bad reputation. There's a connotation that keep those chemicals away from me, but actually you can't do that. Many chemicals are essential for life, and we're made of chemicals. So just keep that in mind. It has a very, very broad definition. A chemical reaction, as shown below, is the process by which one or more substances change to produce one or more new substances. So see that little arrow on the bottom pointing to the right? That is called the yield sign. That means you had something before on the left and afterwards on the right, just like we read when we read a book. So the chemicals on the two sides, as long as they're different, not exactly the same, you know it's a chemical reaction. So there are 118 flavors of matter, but each flavor can come in a different state. So that complicates it a little bit. We call these the states of matter. They are the physical forms of matter. And Generally, we consider there to be 4 of them. You probably at least know 3 of them. And then the 4th one is one I want you to definitely be aware of. They are solid, liquid, gas, and plasma. So I'm going to go through the differences between those. Should be a review, at least for the first 3. And if you're not aware of plasma, I think it's a shame that many people are not. And I'm going to make sure you at least have some knowledge of it. Now, the problem we have in trying to observe chemistry, trying to understand chemistry, is that all we can really see is what is called macroscopic. Macroscopic refers to what you can see with the unaided eye or with a little bit of help, like with a magnifying glass. Macroscopic is what we see in our world. Looking around, anything we experience is on that big scale, the big scale. Unfortunately, chemistry doesn't really operate on that scale. The workings of chemistry happen way down deep on what we call the microscopic. Now notice there's only one letter difference between those two words. Microscopic, think of a microscope. It's things you could only see through a microscope, and some of them actually you can't really see with a microscope. It just implies the small view, the small scale. So if we could see what those individual atoms were doing, chemistry would be so obvious. It'd be, oh, I see it, there it goes. But unfortunately, we usually can't, because even if we can zoom in like an electron microscope or something that lets us see on that really tiny scale, well, the problem is things are moving. So we haven't really worked that out, a way to see chemistry happen. So a lot of times we have to use models. I'm going to be using models to represent what those little molecules, atoms are doing on that microscopic scale. So the macroscopic scale, look at Godzilla on top, that's the scale that we live on. Even though he's bigger than we are, it's still kind of on that giant scale, lumbering around. Okay, we're like giants lumbering around compared to the world of chemistry, which is way down deep on the microscopic, like I've got Ant-Man on the bottom. Okay, obviously if it was truly microscopic, you wouldn't see him, but I needed to represent it somehow. So this is the issue with chemistry. We are like detectives living on the macroscopic plane, trying to understand what is going on in the microscopic world. So what we have to do, just like detectives, we look for evidence. Evidence that something is going on down there. And that's what we call evidence of a chemical reaction. So when we talk about the 4 states of matter, solid, liquid, gas, and plasma, just remember that each one is organized differently. No matter what the chemical is, the way it's organized defines its state of matter. Most chemicals can occur in any of these states. There's some that actually rarely occur in some of the states, but we're not going to worry about that right now. Okay. The representation on the bottom is with water. Water has a few issues using it to represent the states of matter, but oh well, that's an easy one to visualize, so that's why we're using it. On the bottom left, you see the solid water, which is ice cubes. That is H2O in the form of a solid. In the middle beaker, well, almost middle, in the second one, you see the liquid water in the beaker. Beaker's like a glass cup. And you know what that looks like. And then it's hard to show gas because a lot of times it's transparent. But in the third one, you can sort of see the gas rising off. We'll talk later about whether that's really gas there. Okay. You know what that looks like, or you have some sense of what that is. And then plasma, of course, I'm representing it with the sun because it's not really possible to represent plasma with water. So I'm jumping to something that contains a lot of plasma, like our sun. Now you know what an ice cube looks like. You know what a glass of water looks like, and you have some sense about gas. It's all around us. But do you think about what it's like on a microscopic level? So that's what I want to get across right now. What are each of those states of matter like on a microscopic level? First of all, what about a solid? In a solid, these are water molecules, those H2Os. And notice, well, they are moving because it turns out molecules are always moving. until you get to a very particular point called absolute zero. So they are moving, but not much. And when molecules aren't moving much, it turns out they like to grab a hold of each other. They like to sort of latch on, link together, and form some kind of structure. This is the beautiful structure inside of an ice crystal. This doesn't fully represent it because this is a flat image, like a cut through, and you would really need a 3D model to represent it better. But just the point is that the water molecules are barely moving and they are linked together. So that's what gives solids their properties. In a solid, you have a fixed volume and a fixed shape. That means it doesn't change its size and it doesn't change its shape. All right. This results because they're all linked together. They're very tightly organized. They're in a nice little structure. Usually it's a crystal structure, or it could be a glass structure. And they're not going to change their shape other than if you sort of shatter the glass or break something apart. It's not going to just change its shape on its own. And that's the definition of a solid. However, if you add enough energy to a solid, you can change it into a liquid. Now notice it's very different. If you look at those little water molecules in a liquid, what happened to all that organization? The organization is essentially gone now, and the little water molecules are moving faster. So fast that they can actually slip past each other without latching on. That's why liquids sort of flow around. That's why they just don't stay in one place. That's why they don't just keep one shape. Okay. However, remember those water molecules, they would like to grab a hold of each other, and they are trying to, so they don't leave a lot of space between each other. They're trying to stay together, which is why liquids have a constant volume. So a liquid has a constant volume, a fixed size, let's say, but not a fixed shape. As you know, if you knock over a glass of water, it doesn't stay in the cup. It flows right out. Okay, it doesn't keep the same shape. It keeps the shape of its container, as we say. So you probably knew that. But now, if you didn't know why, you can picture those little molecules and the way they're moving. What about if you were to add more energy? If you added enough energy, those water molecules would begin to bounce off of each other. And if they bounce off of each other, you would wind up with the third state of matter, which is a gas. Now, it would be moving way faster than this. I just tried moving it faster, and it all becomes a blur. So try to imagine this is a slowed down version. And notice they're colliding. They're bouncing off of each other. They're bouncing off of the sides of the screen, which is, let's say, the container. And there's big spaces between them. Well, that's why gas is so, what we call rare. That's why gas is so thin, right? It's because there's big spaces there. You didn't see those in solids and liquids. That has a big result in the way gases behave. So gases can spread out. They can be squeezed closer together. They no longer have a fixed volume. So gases have no fixed volume and no fixed shape. And you probably knew that, but maybe you didn't understand why. Maybe you didn't picture those little gas molecules and the way that they're behaving. So try to take a moment and picture the gas molecules in the air around you. Try to imagine them moving fast, bouncing around with lots of space between them. See if you can imagine that. That's something we often have to do in chemistry. So what about the fourth state of matter? Well, plasma is the fourth state of matter. And in order to get plasma, well, unfortunately, water will not remain water if you convert it into plasma. If you take water and you take it to an extreme high energy, like let's say like in the sun, where there's plenty of energy, well, it rips apart the water molecules. And not only that, it rips apart the atoms, it rips apart the electrons. So when you have plasma, what you have is kind of a soup, okay? A fast-moving collision of the parts of the atoms that made up water, let's say. All the different parts. The leftover of the oxygen, leftover of the hydrogen, and the electrons. And it's flying around like crazy. And that only happens when you have extreme conditions, okay? So plasma is called the fourth state of matter. It's different from a gas. Why? Because plasma does something that gas does not. I didn't put it on here, but plasma also has no fixed volume and no fixed shape. And the thing that plasma does that gas will not do ever is conduct electricity. So plasma is the fourth state of matter. It makes up stars, so it's actually the most common form of matter that we know of, other than maybe dark matter, in the universe, because most of the matter we know of is bound up in stars or in nebulae. It is formed when high temperature and high pressure strip off the electrons from a nucleus, and it makes fusion possible. We usually talk about fusion. This time, we're pressed for time. I'm not sure if we're going to get into much discussion of fusion like we normally do. But because it strips off electrons, that's why you can no longer have water molecules in plasma. It conducts electricity. So whenever you see a lightning bolt, we don't get a lot in Southern California. We get about the fewest in the world outside of, if you're over the ocean or in desert zones like the Sahara Desert, we get some of the fewest thunderstorms a year in Southern California. But every once in a while you'll see one, or if you've lived anywhere else, you've seen them. That's plasma. We do get plasma on Earth, and it's incredibly energetic. It's at really extreme conditions, like a lightning bolt. That's plasma. Or think of a star as plasma. We can generate plasma artificially, okay? This is not the same kind of plasma that is in blood. That's a totally different use of the word. They call the essential part of blood, the sort of the background in the blood, the plasma. That has nothing to do with this kind of plasma, except for the word origin. So those are the four states of matter. And it turns out that any chemical can be in any of those four states. So just changing between those, like solid to liquid to gas, isn't really changing your chemical. It's just changing the state that it's in, or the phase. They also call it a phase of matter. So how do we know if there's been a chemical reaction? Well, one thing is to define the other kinds of reactions. Those are physical changes. A physical change is any change where the identity of the substance doesn't change. Think of chopping wood. You're breaking it up into smaller pieces. Smashing up rocks with a hammer, okay? Cutting up paper with scissors. Those are all physical changes. Going between the different states of matter, changes of state are physical changes. So melting an ice cube, boiling water, those are physical changes. They're not chemical changes because the chemicals you had at the beginning are still the chemicals you have at the end. So how do you know on this big macroscopic scale we live on if there's been a chemical change? Well, we look for evidence. Chemical changes occur when the identities of a substance change and new substances form. So some of the pictures on the bottom are showing chemical changes. Like you can see on the one on the left, you're getting bubbles coming out of there. Usually that's a chemical change. Not always, because you could boil water and get bubbles. But generally, if you see bubbles just coming out of nowhere, they call that evolving a gas. Well, that's probably a chemical change. A change of color is a chemical change, almost always, because colors are produced by the ways chemicals reflect and absorb light. And if they reflect and absorb light differently, it's got to be a different chemical. So almost always a change of color is a chemical change in B. And then in C, obviously a flashy, like firework, or this is the thermite reaction that we do as a demo later. Normally we do that as a demo. Well, that's an obvious chemical reaction. But some chemical reactions are so subtle, like in D, you wouldn't even know anything had happened unless you put in an indicator, like a few little drops, and the color they change will tell you, oh yeah, something did happen. Like this indicator, you might be able to barely tell there, turned light purple. That tells us that something must have happened there. So chemical changes can be dramatic or subtle, and we have to look out for them. Here we see an example of a word equation for a chemical reaction. Notice that the chemical on the left in green, mercury 2 oxide, is different than the ones on the right that are in red, mercury plus oxygen. This is the textbook cover for our old textbook, and it has an image of this very reaction. Notice there's a little test tube with a red material in it. That red material is the compound mercury oxide. It is being heated over a Bunsen burner, causing it to decompose, break apart into two components. If you look very, very carefully on the right in the test tube, you can see a little dollop of the liquid mercury forming. The oxygen is escaping the test tube. It's going right out into the air. So that's an example of a chemical reaction. Notice that what's on the left side is different than what's on the right. So what do we call the two sides? The chemicals that go into the reaction are the reactants. They are the chemicals, or in this case, there's only one chemical, mercury oxide, that reacts. They're always on the left before the arrow. They are used up in the reaction, or at least mostly. On the right side, after that yield sign, you have the products. Another name for the yield sign, you could read it as produces, and the things that it produces are the products. The products are the substances on the right-hand side of the arrow. They are made by the reaction. So if you can see the formula for a chemical reaction, you know that one has taken place because the reactants are different than the products. But many times we cannot see this. Because of our macroscopic big scale, we sometimes have to look for evidence that we can see. To determine if something is a chemical change, we need to know if the chemical formula changes. So we have a list of evidence that tells us if it probably happened. A physical change is when you only change the phase, which is also the state of matter, or the shape, like we said, chopping wood, ripping paper, okay, just moving things around isn't necessarily going to change your chemical formula. Melting an ice cube doesn't change the fact that it's H2O. So we are on the macroscopic scale, and we want to see macroscopic evidence that something is going on the micro scale, that there was a chemical change. So the evidence that a chemical change may be happening generally falls into one of the following categories. These are the kinds of evidence we look for. One of them is the evolution of a gas. That means making bubbles. Without heating it up much, if it suddenly starts making bubbles, it's probably a chemical change. Formation of a precipitate. A precipitate is something that is thrown down to the bottom, like precipitation is thrown down from a cloud. In a chemical reaction, precipitates are normally a solid that is thrown down to the bottom of the beaker, so forming a solid. The release or absorption of energy, so if you detect a change of energy from the system, usually we do that by measuring temperature, but it could also be in the form of light. And again, change in temperature, giving off light, that's a good sign that there was a change of energy. It could also absorb, there's other things that can happen that aren't as obvious, but you can usually detect that if you have the right equipment. A color change is almost always a sign of a chemical reaction because different chemicals reflect and absorb light differently. So if you see a different color, it is most likely another chemical. And a change of odor is one of the best because when we detect a smell, an odor, we are detecting particular chemicals or parts of them that our nose can sense. And if there's a different smell, it's got to be a different chemical. That's a really good one. Even though we don't always want to smell chemical reactions, oftentimes the products of the reaction can be a little bit hazardous or toxic. So we want to notice if we do smell something, but we don't want to go out of our way to try to smell a reaction. Okay, we want to maybe waft it towards us to tell. So those are the evidences of a chemical reaction. Those are the pieces of evidence for a chemical reaction. If you see any of those, it was probably a chemical reaction. If you don't, then it's probably a physical reaction. That is the end of the notes for today.